Proof is a topic that relies heavily on rearranging and simplifying formulas. Ultimately, any proof question is basically wanting you to rearrange said expression involving algebraic letters to prove a point, surprise, surprise. This may be that you want to prove that a given expression is always a multiple of 5. Well, in order to prove that it's a 5, let's say that after some simplification, you got 45 n squared. You could show, therefore, that that's a multiple of 5 by just factorising 5 out, leaving you with 9n squared. What this is saying is that regardless of what n is, the overall result will always be in the 5 times table. It will always be a multiple of 5. Similarly, we can use this concept to show if something is always a cube number, for instance. Say when you'd finish your simplifying, you got 8a cubed. You could show that that is expressed as 2a all cubed. Therefore, regardless of what a is or what 2a then is, everything is being cubed. The whole value is therefore a cube number. You'll notice here it's always in terms of algebraic letters. That is because, as I may have already been suggesting in how I'm wording this, that this is showing it works for any given value of n of a, of whatever the letter is. You are not going to be giving a value to these letters when you're doing the question. If you do that, then yes, you're demonstrating it may work for that value. It may work when n is 2 or when a is 7. But you're not showing that it always works, and you can't then test every single actual value because there's infinite of them. So we have to keep it in terms of these algebraic letters. We're just going to be rearranging and rewriting, simplifying to exemplify the point we're trying to prove. For instance, though, if we had this whole expression to begin with, because again, we're not just going to be starting with the 45n squared. We're going to be starting with something that we need to rewrite to get to that point. So to prove, and then for all values of n, that n plus 3 all squared minus n minus 3 all squared is even. Well, first of all, let's just start by expanding. And these kind of questions always suggest, almost always suggest that you expand first and foremost, unless you can tell there's going to be a specific, like you can cancel through by a given bracket. In this case, so n plus 3 squared is going to be n plus 3, n plus 3, and then the n minus 3 squared, n minus 3, n minus 3. Timesing these out by expanding your double brackets. So first times first, so n times n is n squared. Outer, n times 3 is 3n. Inner, 3 times n is another 3n. And then 3 times 3 for the last is 9. This all is then being minused from the expansion of these other brackets. So n times n is n squared. N times minus 3 is minus 3n. Minus 3 times n is minus 3n. And minus 3 times minus 3 is once again positive 9, because a minus times a minus is a plus. If we're then taking these away from each other, okay, well, n squared minus n squared, that's going to cancel. 3n add 3n is going to be 6n. Here, minus 3n is going to be minus 6n. 6n minus 6n. Again, you've got a minus and a minus turning it into a plus. So it's actually 6n add 6n. That gives us 12n, and then 9 minus 9 again cancels. So we've got that this all just becomes 12n regardless of what n is. To then show this as even though yes we can see 12 is an even number, you want to make it very clear, explicit, factorize 2 out, because 2 is what determines if a number is even. So yeah, this question could have just as easily just asked, show that this is a multiple of 2. You factorize 2 out at the very end, you show it has been times by 2, therefore value is even. Similarly, over here on the right, even though this is now in a fraction, we're going to be using very similar principles. We're going to be expanding the brackets on top first. So we're going to have n times n, which is n squared, then n times 2, which will be the 2n. 2 times n is 2n, and 2 times 2 is 4. That's our first bracket expanded. Then minus n times n is n squared, n times 1 is n, 1 times n is n, and 1 times 1 is 1. And that's all for now, still over 2n squared plus 3n. Just bringing together like terms, n squared minus n squared is going to cancel. 2n add 2n is 4n. N add n here is 2n. So 4n minus 2n, that's going to be just 2n. And 4 minus 1 is going to be 3. So it's 2n plus 3 over 2n squared plus 3n. Well, we can already see now the top and the bottom are very similar to each other. So how can we make them the same things? If they're the same, they can cancel, we can simplify. If we were to factorize n out of, on the bottom, that's going to leave us with 2n plus 3, that being 2n plus 3 on the top. And now, yeah, this just cancels with this, to leave us with 1 over n, which is what the question wanted us to show in the first place. The benefit of doing these kind of prove or show that questions is we know where we need to end up. We know if we'll have gone right or wrong, depending on how we finish. Whether that's because we see exactly what the fraction is going to be, so in this case we know it has to be 1 over n, or in this case even, we just know we need to get to some point where we can factorize a 2 out. You're never going to use these answers in the working though. This is just saying that you're going to end up here. Don't try to incorporate it in the working itself. Let's see how you get along with a question of your own. We just clear up this space here. Now, what if you were given that 2n plus 3 squared minus 2n minus 3 squared is a multiple of 8? Could you prove that? Pause the video, have a go for yourself, and then when you're ready, press play again and we can compare. Alright, so first of all, as we've kind of did down here, we're going to want to expand our brackets first. So here, expanding this, we're going to have 2n plus 3, 2n plus 3, and here minus 2n minus 3, 2n minus 3. First by first, it's going to be 2n times 2n. That's 4n squared. Then if we do 2n times 3 for the outers, that's going to give you 6n. 3 times 2n for the inners is 6n, and then 3 times 3 for the last is 9. Then for the other ones, 2n times 2n is going to be your 4n squared again. 2n times minus 3 minus 6n minus 6n plus 9. Taking these away from each other, just with like terms, 4n squared minus 4n squared is nothing, it disappears, it cancels. 6n add 6n is our 12n. Minus 6n minus 6n. So another, well now minus 12n. So 12n minus minus 12n. That's 24n. And then 9 minus 9 cancels. So all we have is 24n, which we can show as a multiple of 8 by factorizing 8 out, leaving it as 8 lots of 3n. So regardless of what n is, the overall number is times by 8. Okay, with that, let's have a look at an actual exam question. Now, the questions may not always give you the expressions in terms of actual numbers and symbols already that you're going to have to be working with. You may have to work out what the expressions are yourself first. Here the question is asking to prove algebraically that the difference between the squares of any two consecutive integers is equal to the sum of these two integers. So we have to just unpack this sentence. Okay, what's going on? The difference, so we're going to be minusing between the squares, okay, so we're going to square numbers and minus them, of two consecutive integers. Okay, well, integers are whole numbers, and consecutive means one comes after the other. So that's 1 and 2, or 13 and 14, 56, 57. So we're going to square two numbers that come after each other, then minus those squares from each other, and show that's the same as just adding those two integers together. Once again, we're not going to be using actual values for our numbers. We're just going to be using algebraic letters. Let's use n because it's kind of traditional. So if n is one integer, the next consecutive one could be written as n plus 1. Or if you prefer n minus 1, it's going to end up giving you the same thing. Squaring these then, okay, well, n plus 1 squared, so n plus 1, n plus 1. So again, expanding the brackets, going to get you n squared plus n plus n plus 1. And then this is going to minus, well, n squared is just n squared. So this all just take away n squared. That means the n squareds cancel, leaving you with just 2n plus 1. Okay, we have our differences of the squares, therefore. Let's now also work out what the sum of the two integers are. And simply adding these two together, you've got your n, add your n plus 1. That's going to give you 2n plus 1. Oh, look. They equal the same thing. You have proven the statement. Just one last thing I want to say before we finish this stuff, because we've got a 2n plus 1 here. Some questions, rather than just saying consecutive integers or something like that, they may specify odd numbers or even numbers. In those cases, we can't just say, okay, our number is going to be n, because n isn't definitely odd or even. It could be anything. If you need something to definitely be even, then you should use something like 2n, because then regardless of what n is, this whole expression is even because it's been times by 2. And if that's even, then odd would be 2n plus 1 or minus 1, because an odd number is just 1 on either side of an even number. I mean, you could do 2n plus 3 if you wanted, 2n plus 53 if you wanted, but as long as it's an odd number. Yet, if you're going to be doing consecutive odd numbers, again, you just have to think, consecutive odd numbers, they're still next to each other, even though they have a difference of 2. So that would have to be 2n plus 3. Again, think that 1 and 3 are the two consecutive odd numbers. So if you had 2n, which was the same even number, you add 1, you add 3, they will be the next two odd numbers along.